Is my voice clear? Audible to all of you?
Yes, sir. Yes, sir.
Yeah. So, radical chemistry is highly interdisciplinary, and to understand well, actually, means we just need to understand basics of organic chemistry, inorganic chemistry, as well as physical chemistry, and some spectroscopy related to physical chemistry. But it's extremely interesting because of its multi-dimensional applications. And today I'll be actually talking to you on very basics of radical chemistry, showing some of the applications today, very few applications. But then in my next uh, presentation next week on Friday, I'll be presenting mostly my work, our research group's work on radicals and radical ions, as well as their applications. So today it will be very basic. So I'll like that you interfere in between. You ask me questions. You can stop me, um, and means can I get an idea that in this uh, meeting that how many of you are from organic chemistry, inorganic chemistry, physical chemistry? Is it almost equally distributed? Something like that. Can you tell me?
More organic chemistry.
Mostly are from?
ज्यादातर participant
थर्टी
organic
थर्टी
chemistry.
है ना वो लिस्ट तो है
Okay, okay. Thank you so much. Yeah, so it's actually so mostly it will be organic chemistry based, but then we'll have very small things which are very basics of physical chemistry. Because without physical chemistry, we cannot understand the basics of the radical chemistry. So the outline is following. The brief history of radicals. I'll give you a very brief history of radicals. And what is the homolysis and heterolysis of bonds? Because bonds are very important. How important is the bond dissociation energy? What are the types of radical reactions? We must understand the molecular orbital picture to understand the radicals and their stabilization. So stability of radicals comes after we understand the frontier molecular orbital picture. Then I will discuss with you some of the important reactions of radicals. Selectivity of radical reactions, which is something very interesting, that how radical reactions decides itself, chemoselectivity as well as regioselectivity. It's very interesting. It seems that radicals have their own minds, basically. They're very intelligent. To understand radicals, their structures, and their characterization, ESR spectroscopy is very important. So I'll discuss with you briefly and also some of the applications. Very few applications today. So I'll start with one of the earliest radical. Can you tell me, one of you, which was the first earliest reported radical, organic radical? Any one of you?
ओनली मिथाइल
What was the earliest radical known? And who was the person who discovered it?
गूगल करना है
I like to interact with you, so if you can please let me know. So it is the radical reported by Professor Bomberg, and it is actually known as Bomberg's radical. And he reported this in 1900 in the Journal of American Chemical Society. So this was the radical. You can see this is a triphenyl butane compound. When he treated this with silver or zinc dust in benzene, he could dissociate this carbon hydrogen bond and he could make this molecule one dot. Radicals have a unpaired electron. Remember this, radicals will have a unpaired electrons. Why this unpaired electron has formed? The reason is that the carbon hydrogen bond has been dissociated And the
Homolytic.
electrons that was formed by the carbon-hydrogen bond has now dissociated into two electrons. So one H dot has formed, and along with that, this triphenyl methyl radical has formed. So this is a homolysis of this or homolytic cleavage of the carbon-hydrogen bond in presence of the metal. The metal dissociates this carbon-hydrogen bond, and this from this reaction, Professor Bombard called this as a free radical. So you must be knowing this term. From there itself, this term free radical came. This radical is susceptible to dimerization, and it dimerizes from the para position. So it dimerizes from this para position. So that means this structure can undergo some resonating structures. It can form some canonical forms, and this spin of the electron can come over the ortho position as well as the para position. Ortho position is sterically hindered. So para position, from para position, it dimerizes with this form radical. So from para position, another molecule of this radical dimerizes to form this. But interestingly, this dimerized product was not described by Gomberg. This dimerized product was described only until 1970. So there was a confusion because Gomberg simply said that this radical is only dimerizing from here. So that was his report, because those days in 1900 there was no NMR or EPR. So it was his assumption that this radical, free radical, is dimerizing from this. But NMR studies in 1970 showed that the dimerization is happening to the para position. So these are the reports by Professor Bombard. And I would suggest you that you can read this book by Professor Hicks. This is a wonderful book on stable radicals, fundamental and applied aspects of odd electron compounds. So I will now show you the original manuscript written by Professor Bombard, which was published in JACS 1900. So this was the original paper. You can see here that this was the structure he reported. Don't think that this is a alkyne bond. It was because those days there was no ChemDraw. So here it is all typesetting. So it was the triphenyl methyl radical is drawn like this. So carbon with 3 bonds of the phenyl group. So this was his report. You can see this, and he says here itself that the original evidences what he provided leads him to believe that a free radical of this type has formed in presence of zinc or silver. And then he goes on to say that the radical refuses to unite with one another of its kind because it is very apparently stable. It can be kept both in solution as well as in the dry crystalline state for weeks. But it can dimerize to form this hexaphenyl ethane. So as I told you in the last slide that it forms this type of a dimer. But then he goes on to say that this hydrocarbon is so unstable that mere exposure to air is sufficient to break it down. So that was his assumption. Then he proved this structure by doing simple reactions. When he reacted with oxygen, he could get this type of a peroxy bond. When he reacted with iodine, he went on to get this type of iodo triphenyl methane compound. So he, by doing simple, very judicious or intelligent reactions, he could prove the existence of this radical. But very interestingly, when he concludes this paper, he writes down this thing. It's so interesting. This work will be continued, and I wish to reserve the field for myself. It's so interesting, you see. So he makes an assumption already that he has found out something very, very interesting, and he wishes that nobody actually starts working on this. He wants to reserve this field for himself. This is something very interesting. So now I will show you some of the very interesting radicals, other radicals which have come upon. These type of radicals have come upon. This is Chichi-Babin type of reactions. Chichi-Babin type of a neutral radical, diradicals. I hope you know this radical. This is commercially available in many of the with organic companies which sell organic compounds. This is called the diphenyl hydrazine picaryl radical, DPPH radical, diphenyl picaryl hydrazine. So this is a hydrazine moiety, is a diphenyl, and this is a picaryl moiety, 2,4,6 trinitrophenyl. This is a phenylalanine moiety, phenylalanine radical. This was also reported in a Nature paper around 1960s. This is a famous galvanoxyl radical. This you know, very famous. This is also commercially available radical called tempo radical. Tetramethyl piperidinol oxide radical. This is a Hurtazyl radical, and then there can be this type of also conjugated radicals. So many types of radicals have been known, but remember that radicals, because they have unpaired electrons, they are very susceptible to reaction and pairing of the electrons. So they are susceptible to moisture, they are susceptible to oxygen, and they are pretty unstable. Can any one of you tell me that why these are called free radicals? Why Gomberg called these systems free radicals? Any one of you?
Highly reactive. Highly reactive. It
what?
forms a bond with
Why you think these are called free radicals?
highly reactive. And it can easily forms a bond with another molecule. When it propagates the reaction.
Yes, exactly. So it is very free to form a bond. It is free to react. It is free to pair with another molecule. So its electron is free for pairing with another electron. That is the reason Gomberg very intelligently called it as a free radical. Now you think of some other systems. I just described you a free radical. This is another type of a radical called the organic radical anions. So as I described with you that the organic radicals can have neutral or free radicals, that means there is no charge in them, no electronic charge. These systems, organic radical anions, can have a negative charge along with the unpaired electron. And there are multiple radical anions which are known. This is one of the earliest radical anion, which you know is a benzophenone type of a radical anion. Then there is this anthracinyl radical anion, naphthalene radical anion. This is a very famous radical anion called tetracyanoquinodimethyl radical anion. I'm sure you know this radical anion because this was reported around 1970s and 1990s to be organic superconductor. This TCNQ, tetracyanoquinodimethyl based radical anion. Along with this is also very famous radical anion called the DDQ, right? Dichlorodicyanobenzoquinone. This is also a very famous radical anion. This is a naphthalene diamide based radical anion. Then there can be borate type of radical anions, phosphine based radical anions, right? And porronine based radical anions. Now for radical anions to form, you need some certain condition. You